tends to take a broader focus in data visualization, not just looking at data analysis and data scientists, but rather how do we use visualization for communication, particularly with audiences who have maybe less technical, less domain expertise. And in particular, some of our recent work has taken a focus on uncertainty that you'll be talking about today. And a lot of this work has won numerous awards, both in academic venues and also via an NSF Career Award and things like that. So please join me in welcoming Jessica.
Thank you. Thank you for inviting me. I'm really happy to be here. And I'm calling my talk Seeing What We Should Think Through Visualization Interaction. I'm going to talk about work in my lab for the last few years. It's kind of building towards a vision of how visualizations work in the world. But I think as I go, maybe you'll see what I mean by this. So visualization use has become commonplace both in the media as well as in the more conventional analysis settings. And in both cases, I think it plays an important role in helping people form impressions about the true state of the world, which data is a proxy for. And so by looking at visualizations, we can kind of make judgments about what is signal, what is noise, and we can do this with the help of the perceptual system so it's more efficient. The question I want to pose today is, how do we judge whether a particular visualization is useful or helpful? Because we know it's certainly not the case that all visualizations of data are going to be useful. So for instance, we've all seen particularly bad examples where we could say for sure it's not effective to show percentages that don't sum to 100 in a pie chart. But I would say that most visualizations are not so easy to dismiss in terms of whether they're useful or fulfilling their function or not. And that's because they're the outcome of reasoning about design trade-offs between different possible sort of criteria where there may not be a single optimal design. So we could call visualization design a wicked design problem, and that there's no clear stopping rules often. Solutions can be good or bad, but not necessarily true or false, etc. And so as a designer, I might sort of try out different ways of aggregating data, different ways of adding context to data, and often it's not clear sort of what is best. It depends on my goals, what I'm trying to communicate, which makes evaluation with a formal framework difficult often. But you would think that visualization researchers have sort of figured this out, how to evaluate visualizations, at least using users, because we can rely on sort of how people actually make decisions with visualizations to evaluate effectiveness. And so to get a sense of the state of the art in visualization evaluation, I recently looked at 86 uncertainty visualization evaluations. I think uncertainty visualization is a particularly challenging form of visualization in that we know uncertainty cognition is difficult, and so we would expect some of the best evaluation techniques are most sophisticated. But what I found was a little disappointing in that 43.3% of the evaluations I looked at used self-reported satisfaction measures to measure or assess performance. So basically, if you want to know if a visualization works, you ask the user, was it useful, or did it help you on your task, or did you enjoy using it? And we know, I think, that this is kind of a shallow and not very accurate way to think about sort of when visualizations are useful. So for instance, there's a lot of work in judgment and decision making that says that people try to avoid uncertainty because it makes their judgments harder. But I don't think we would conclude that showing uncertainty in a visualization is just by necessity bad. On the other hand, another third, roughly, of all of the studies or evaluations I looked at calculated error or bias relative to some true answer. So some sort of accuracy, often in how well people could read data from the visualization. And that can be useful, but I think there's also this gap that we know exists between whether people or what people perceive in terms of whether they get the values and then how they act based on them. So for instance, we know people are boundedly rational. They operate on constraints like time or money. We also know people have prior knowledge often about the data, especially when we're presenting data in some of these casual contexts like data journalism. People have seen information about the topic before, and their prior knowledge and even their preferences, what they want the data to look like, for instance, on climate change, may impact what they take away from a visualization. And so I think the trends in evaluation suggest kind of an underlying idea of visualizations as having this sort of simple use where we just want the data in the person's brain at the end of the day, this perfect replica. The person should be happy. And it sort of sets up this more underlying kind of set of assumptions where we think about sort of the visualization as showing the truth or the data as being exactly kind of what we need, where all of the other preferences and prior knowledge that a person is bringing are noise that we ideally wish would just go away. And so as a visualization researcher, I've been kind of thinking for the last few years about these assumptions that I see in evaluation and other visualization design practice, and trying to understand, well, how could we go beyond this, and what kind of frameworks might help us understand how visualizations facilitate thinking and decision making, because that's really sort of what they're designed to do. And so in kind of thinking through sort of places where I think visualization interactions are often shallower than they need to be or not necessarily focusing on the right thing, it's become clear to me that I'm working more in my work towards kind of looking for a framework for evaluating and thinking about visualizations that really looks at rational inference and thinks about what that should look like. And in particular, I've realized that though it wasn't my goal to begin with, my work is kind of taking me more towards this Bayesian vision for visualization, where we're thinking about using Bayesian statistical inference as kind of a framework, how people update their beliefs based on new information. And so one of the key components of a Bayesian statistical inference approach is that we come in and define priors, which basically represent what we know about some parameters, such as the true job growth in the country or the true change in global temperature, before we see the data. So we have some notion of, based on our past experiences or past data, what values are not even plausible, what values are more likely. And then we also are going to identify a likelihood function in Bayesian statistical inference, which reflects the information about the parameters we care about that are contained in the data, assuming some process, some probability model that generated the data. And so the likelihood function is sort of a nice way of quantifying the uncertainty in the data and quantifying really how much signal we're getting from the data. In a Bayesian statistical inference framework, we're going to take both the priors and the observed data and use that to calculate posterior beliefs. So what people should believe or what we should believe given the priors we had, what we thought was plausible, et cetera, coming in, and the observed data. And so we can sort of use Bayesian, this Bayesian framework as a prescriptive framework where we can actually, if we can elicit people's own actual posterior beliefs or infer those from visualization judgments and elicit or infer their priors, what they believed coming in, then we can look at this discrepancy. And so one possible thing that we gain here is a better way for thinking about evaluating visualizations. So maybe much of this isn't clear now, but what I want to do in my talk today is take you through sort of how I've gotten here, and then at the end I'll talk a little about current work where we're actually sort of doing Bayesian modeling of visualization interpretation. But how I got here first was thinking about, well, what would happen if you did ask people to interact with and even represent their prior knowledge or beliefs about data in a visualization interaction. And so I'll talk about what we've learned about how simply asking for people for their priors kind of changes the outcomes of interaction. And then secondly, I've been doing a lot of work on thinking about how do we align subjective sort of senses of uncertainty in the data with statistical accounts of uncertainty, because we know people have a hard time understanding uncertainty, and how do we develop better visualizations to help them with this. So this first line of work I'm going to talk about today is one that my PhD student at University of Washington, my former institution, has been leading, where we've basically been looking at and asking a number of questions aimed at understanding what happens when you ask people to think about their prior knowledge during visualization interaction. And to give you a sense of where we started thinking kind of how would you even get people to bring up their prior knowledge in an interaction. And one thing that became clear is that, well, you could ask them to just make a prediction about the data in a visualization. So you could imagine, for instance, I'm a data journalist. I'm going to show you some data on median home prices in a city like Seattle. But imagine rather than just showing you the data by default, I asked you to think about what you would expect this data to look like. So if you take a moment and think about what would the median home price in Seattle look like in 2015, 2016, 2017, I'm guessing you kind of have to think about what you know first maybe about home prices in the US, and then maybe what you know about Seattle in particular as a market. So now if I were to show you the actual data, I'm guessing that you can't help but sort of think about what your prediction was relative to that data. So you're going to be noticing where you overestimated, underestimated, simply because we've kind of called your prior knowledge to mind, or your best prediction for this. And so this is how we sort of started thinking about one possible way to actually graphically elicit people's thoughts and prior knowledge about data, or predictions about data. And so we wanted to know how an exercise like this simple graphical prediction task, changed outcomes of an interaction, and in particular, how well people remembered information as a simple proxy for comprehension. So we're going to have people make predictions using graphical interfaces, but we also looked around in some of the literature, particularly in educational and cognitive psychology, about ways that other researchers in learning contexts, for instance, have tried to get people to reflect on their prior knowledge as they're getting new material. And there's a pretty robust effect in educational psychology around self-explanation, where if you want someone to understand new material, which is often in a text format in the studies that have been done, you should ask them to explain it to themselves. And by explaining it to themselves, they are sort of forced to realize where there are gaps in their knowledge. And this causes them to learn better. And so they remember the information better, and they do better on tests, et cetera. And so we wanted to use this as a comparison point or an alternative way to get people to reflect on prior knowledge in a visualization interaction. And finally, the theory behind self-explanation and why it works right now is that it's getting you to notice this gap between what you thought and what you now see in the new information. And so we thought, well, potentially providing feedback, automated feedback on how well someone did when they predicted data in a visualization might also add to any effects that we see of that kind of interaction. And so we have these three sort of categories of techniques that we used in an initial experiment, which again is focused on just how well people recall data. We're thinking about kind of these casual contexts, like when you're presented with data in the news. And we formulated 4 different study conditions to try to identify the effects of things like just explaining the data to yourself, so having to explain what you see, just making a prediction before you see the data in a graph, and then seeing the observed data against your prediction, predicting the data in a graph, and then having to explain the gap that you see to yourself. We thought potentially is there a larger effect there because we're combining these techniques. And also predicting the data in a graph, seeing the data against your prediction, and getting some automated feedback about where you were over or underestimating, et cetera. And we wanted to compare these to the baseline that represents kind of the status quo right now, where usually if you see a visualization anywhere online or in a report, you just see the data automatically. So we needed to choose a visualization format and a specific data set for this first experiment. And so we decided on something that we thought was sort of moderately complex, certainly still simple enough that you might see something like this in a data report or something online, where we have one ordinal variable along the x-axis, a categorical variable shown in color here, and a quantitative variable. And these kind of plots are commonly used in psychology, for instance, as interaction plots, and as well in the physical sciences. And they, like most visualizations, allow you to think about specific values. So we have a limited number, only about 6 values here, but also about trends, which is where visualizations kind of excel. We also thought about the particular data set that we could use with a format like this, and in particular wondered kind of how familiar people need to be with the domain in order to even feel comfortable making predictions about data. And so here we decided to start with a moderately familiar data set. So we actually did an initial study on Amazon's Mechanical Turk where we had a bunch of data sets and we just had people predict data given descriptions of data sets to get a sense of how different kind of common data sets or data sets that are not necessarily all common rank in terms of familiarity. And so we started with a moderately familiar data set, which I'll show you in a minute, is 2008 presidential election results. But we also ran our study, and I'll report on what we found for a low familiarity data set, scientific experiment data, as well as a data set where a lot of people, at least on Mechanical Turk, had a pretty good sense of what the data was, which was fast food calories. So here is the presidential election 2008 data set that we used in our sort of first run of this study. So we're showing the percentage of eligible voters of different ethnicities who voted Republican in the 2008 election by income bracket, so under $75,000 a year and over $75,000 a year. And we had this data on many states. This is showing you Colorado. And so the procedure in this experiment we did, which is a between subject study, we ran it on Mechanical Turk. We figured out how many people per condition based on power analysis on pilot data. They came to the website to take the study. They got introduced to it. We then, in the prediction groups, had them predict the data before they saw anything. So they got a description of the data set and had to make predictions. If they weren't in a prediction group, we wanted to account or control the amount of time people were spending so that any effects we saw were not just because they spent more time with the information. And so we had them retype the prompt describing the data set. Everybody then saw the data set, the stimuli. If they were in a prediction group, they saw their prediction against the data. If they were in an explanation condition, they had to explain the data to themselves or explain the gap between their prediction and the data to themselves in the explain plus predict condition. Everybody then did a distractor task, which was a spatial folding task, doubled as a spatial abilities task. They did that for about 5 minutes, and then we asked them to simply recall the data. And so they recalled the data, again, by drawing on a graph. We did test other modality text, but I'm just going to report on the visualization conditions to sort of give you the overall gist of what we found. So we wanted to measure people's ability to recall the data in 2 ways. So again, visualizations can convey sort of absolute values. And so we looked at what we called absolute recall error, just this distance, absolute distance between their recalled value and the actual data point. And then we also looked at the slope difference. So independent of the location, how well did they recall the particular trend in the data that they saw? And so our results here for absolute recall error, when we compare to baseline, and for simplicity, in reporting results here, I'm just going to be talking about the mean reduction in error from each of these conditions relative to baseline. These are coefficients from models that we ran, mixed effects models. People were making multiple predictions for us, so we had multiple measures per person. When I talk about reliability also, I should explain, I mean that the 95% confidence intervals don't include 0. But sort of here's the effects we saw. These are estimated error reduction. And we found that all 4 of these techniques reliably reduced error relative to the baseline, and it ranged from 22% to 39%. So even getting someone to just make a prediction worked when we're thinking about sort of how well people got the individual values in the visualization or how close they were on the location of those. When it came to trend error, we found that prediction plus another mechanism like explanation or feedback reliably reduced people's ability to recall the trend in the data, so just the slope we're looking at here and not the location, and that was by 19 or 26% respectively. And so we reran our experiment. This is for the voting results, the moderately familiar data. We wanted to understand how much the sort of familiarity with the domain matters, and we found that these results replicated on a low familiarity data set, something that was very obscure. It was a scientific experiment with some very sort of hard to understand measures. It involved rats. And these techniques also work there. So whatever rhetorical effect they had, just in getting people to think more about maybe the data that they saw, worked. However, in the case of a highly familiar data set, we did not see any differences with the baseline. So when people know the domain very well, it's, there's potentially no real impact for what they remember later of having these techniques. So this first study was just really kind of a way of understanding first how could we get people to even think about prior knowledge in its simple kind of visualization interactions, and how does that impact what they remember? And so one thing that was kind of useful about this study is that while there was a lot of literature and self-explanation in cognitive psychology, no one had really looked at data visualizations. And so, one finding is just that effect is robust even when you're looking at representations of data, not just text learning materials. But we were more excited about this idea that predicting alone in some circumstances, for instance with moderately familiar data, can help someone recall the individual values they're seeing in a visualization, and with feedback can help them recall trends. And so my interest is often in sort of how do we present data to the public in contexts like data journalism. And so I think here, while we have these techniques like self-explanation and educational psych, it's kind of unrealistic to think that you're going to have someone, reading a news piece and you're going to ask them to explain the data to themselves. Whereas something like making predictions, people often want to see how they did. And so if we're trying to sort of get people to think more actively about the data and think about what they knew coming in, this is potentially a viable technique. At least there's no harmful effects that we saw in this study. But we were interested in our kind of next step on this line of work in thinking about this space of possibilities that opens up related to showing other people's predictions. So if you're eliciting a bunch of people's predictions about data in a graph, then you can visualize other people's as well. And we wanted to look again at things like how well do people remember data? Can you look at other people's predictions and also have this kind of focusing effect where you remember the data better? But we also wanted to look at things like how do people update their beliefs based on different kind of constellations of social information and data. And so here we again used the same underlying data set. We decided not to switch too many things in moving to this new study, but we realized before we ran it that for historical election data, it's a data source that's actually pretty relatively low in uncertainty, and that often for presidential elections we end up counting votes in multiple places. And so relative to a lot of the data we see online, I think people are unlikely to question at all things like historical election data. And so we took the same data set here, but we actually reframed it so that people thought they were predicting the 2020 presidential election results. And that's because that's a place where you might start to care a little bit about what other people believe. And so we sort of thought through or speculated initially that there's a few things that might matter in terms of how people update their beliefs based on social information. So first, I might have my own prediction, and maybe I'm predicting for all US voters how many people are going to vote Republican in 2020, and so I make a prediction like this. But there are going to be potentially cases where the observed data is counter to what I predicted. But what happens if social information or other people's expectations align with the data, but also contrast with what I was thinking? On the flip side, what if other people agreed with me but not the data? How would that impact kind of how I update my beliefs or what I remember? Or, how much does it matter how much consensus there is in the social information that you're seeing? If people tend to sort of, on average, agree with the data, but there's more variance between them, does that influence what I take away? So these were the kind of questions we wanted to ask in this study, just to start to get a sense, again, of like what is the impact of having people do this and showing predictions. So we had a condition in our study, a controlled experiment, again, without social information. And then we had conditions that varied whether the social information was congruent with the trend in the data, meaning the slope direction was the same, or whether the social information was incongruent, so it was in contrast to the trend in the data. And then we also varied the level of consensus in the social stimuli that we showed people. And so we wanted to create stimuli that were realistic here, and so we actually ran a study first on Mechanical Turk where we had people make predictions about the 2020 election for several ethnicities, and then we could use those to make social information that was realistic. And so to make our stimuli, we knew what the data was, this election data set we were using from 2008, and then we took the raw social information we got, which looked kind of like this, and separated it into those people who were congruent with the trend in the data and those who were incongruent, and then we simply sampled from the entire distribution for the low consensus stimuli and from the middle two quartiles in the high consensus stimuli, so that it looked like people varied more or less. Because it's kind of unrealistic that everyone agrees on the internet about anything, we also added a few lines in the opposite direction to both. I think we added 3 lines, and we were, the sample size here was 50, I believe, per stimuli. And these are not the actual stimuli, these are kind of icons, just so there's no confusion about that. Here we wanted to look at recall again to see, just seeing other people's predictions also have this kind of rhetorical effect where you focus on the data more. But we also wanted to see whether people were more likely to update their beliefs to align with the trend in the data based on these different configurations of social information. And we wanted to know, do they trust the data more or less? Because if they're not updating their beliefs in a way that mimics what they see in the data, we might expect, well, they don't trust the data entirely. So we did a between subject study, 421 people, again, determined that sample size through prospective power analysis and ran it on Mechanical Turk. Here the procedure, we're first going to get everybody's initial expectations so we know what people thought coming in or what their best guess was for a few different ethnicities. We're going to have them rate their confidence in that prediction. They then examine the stimuli with or without social information and high or low consensus and congruent or not. They then draw their updated expectations after they've seen the data and social information. And then also rate their confidence there, because we want to know, has their confidence changed, and their trust in how accurate the data was. So both of these were visual analog scales, just 0 to 100 sliders. They then played Tetris for 5 minutes as a distraction, and then we had them, it's a good distraction, I guess, we had them recall the data, again, just by drawing. And so that's what that looked like. So I'm just going to go over the results at a high level here. So first off, we found that social information alone was not enough to get people to sort of pay more attention to the data and remember it better, which was our proxy for how much attention we thought they paid. However, when you had high consensus social information, even when it was incongruent, that did result in a reliable difference or reduction in their error in recalling the data later. However, it was the opposite when you had the low consensus. So perhaps just the visual complexity of the stimuli made it harder for people to recall what the actual data looked like, but we saw that their accuracy went down by about 20% there. And then we really were interested here in the impacts of congruency and consensus on how much they trusted the data and how likely they were to update their beliefs toward the trend in the data. And here what we found was that there is kind of a social influence. So when social information was congruent with the data, people tended to trust the data more, about 22%, and they were 1.7 times more likely to update their beliefs or give us these updated beliefs that aligned with the trend in the data relative to incongruent social stimuli. And we found that the degree of consensus did not change this. So it didn't matter if people tended to agree a lot or there was more variance. If the overall signal was incongruent or congruent, that was what mattered. And of course we thought, well, maybe initial expectations explain some of this better. So what people believe coming in might be even more important than social information. And so we tested some hypotheses around that, separated people into those whose initial predictions aligned with the trend in the data and those that did not. And we found that, in fact, when you already agreed with the data, you kind of dismissed the social information. It didn't have any reliable effect on your trust or your updating of your beliefs toward the data. But when you disagreed, there was clear social information where if you disagreed but other people agreed with the data, you trusted the data more, you were more likely to update towards it, and your confidence in your own judgments went down, whereas we saw the opposite. If you distrusted the data, it was almost kind of a confirmation bias. You looked to other people as a signal that the data was inaccurate. So kind of basic social influence was what we found in this second study. And these two studies together and another that we did, which I won't talk about, where we applied this to having people predict uncertainty in experiment results, showed us that first, at an individual level, there appear to be benefits, perhaps rhetorical effects, for things like memory or also the ability for people to make predictions about new data sets simply by having them make predictions. We also found, of course, that there was some effect of social information. So first, it could have this focusing effect when consensus was high, where people remembered information better simply because other people's beliefs were shown. But there's also this influence. So people look to others' beliefs for cues about what's right and wrong. And we could frame this as a potentially negative effect. But I think it's interesting just to note that people, even when they're looking at data sets, they care what people believe about those. So we framed this 2020 election data set as actual model predictions. So we described a model in detail that we were using to make these predictions. And people still thought, well, what other people think matters. And so I think there's no clear reasons not to be thinking about eliciting prior knowledge, such as predictions, in interaction. But before I get around sort of to the current work I'm doing, I want to now talk about this other line of work I've been doing on uncertainty visualization, because I think this is another way we need to reconsider interactions that people are having with visualizations and think about how we can make them sort of align more with kind of rational inference. And one problem that I've been motivated by since I was a PhD student is what I call a crisis in uncertainty visualization, or what I see as a crisis, where we really lack effective tools for helping people reason about uncertainty. Just in my definition here, the possibility that a quantity could take multiple values. So for instance, we often blame journalists who report on scientific experiments in the media for kind of overhyping effects or overclaiming, not showing things like effect size. But I would argue that that is true, but also when we look at the scientific publications, there's a lot of emphasis on, is there a significant effect or not? And there's very little discussion of how big was the effect, or how reliable is it? So was it practically significant? Or if I ran my study again with a new sample, what might the distribution of results look like? And I think one part of the problem is that we lack good methods for presenting uncertainty. So if we look at some of the existing methods for visualizing uncertainty or representing probability distributions, they tend to divide into those that use summary marks to show statistical properties or constructs like error bars and box plots, and those that use visual variables to show a probability or confidence value using area or opacity or lightness or other aspects of color. And both of these approaches kind of fall down on basic visualization criteria for thinking about whether a set of visual encodings is effective. So summary marks, for instance, don't do well when we think about this criteria we use in research called expressiveness. So how well does the visualization express the data, or does it express the data such that my natural interpretation as I look at it is accurate? And so here, a lot of these summary marks are giving us statistical constructs, and they're shown in this simple way on top of the actual data encoding mark, but they imply things that are not true to people. So for instance, there's this well-documented within the bar bias, where people think the part of the error bar on top of the bar is more probable than the part above, and it kind of looks that way, or you could see why they would think that. People also tend to assume that error bars also always mean a uniform probability range, when in actuality that sometimes is true if you're using, for instance, a 95% confidence interval, but not always, for instance, for standard error. And finally, we know people dislike uncertainty and they like to ignore it if they can and just operate based on expected value. I've seen that in many studies I've done. And error bars and summary marks make it easy because you can just sort of ignore it and imagine that it's not there at all. On the other hand, visual variables used to encode things like probability often don't do so well in terms of what we call effectiveness. So how well or accurately can the viewer read the data values based on what we know about graphical perception? And so here, often when we're using visual variables, we're already using the more effective encoding channels, the ones like position and length that people can accurately or more accurately read data from. And so for the probability or uncertainty information, we're left with things like area or aspects of color like lightness, or even things like blur, which people really like the idea of for uncertainty, but is very hard to actually read data from. People can't quantify different levels of blur. And so I think there are these problems, but it's also just difficult to do sort of one of the main things we're supposed to do with visualizations, with these static uncertainty visualizations, which is that it's difficult to make comparisons. So often we're looking at multivariate data, and we care about things like effect size. So what's the size of the effect? Effect size. What is the difference in means, but also how much variance is there, and how reliable is the difference? So if I were to ask you, what's the probability that the bar on the left, if we repeat a data collection, would still be greater than the bar on the right, I'm guessing you'd have a hard time, because these visualizations don't express that information. So again, like I said, since I was a PhD student, I've been thinking about this, but more recently with my own PhD student, Alex Kale at University of Washington, and collaborator Matt Kay, who I've been working with for the last few years, we've been kind of thinking about what are better encodings for uncertainty information that can kind of bring people's subjective senses of uncertainty in the data closer to the actual statistical accounts. And so one of the things I've been proposed back as a doctoral student is hypothetical outcome plots. This is the idea that you could take your data set and present uncertainty in your data not as summary marks, but as a set of actual possible values you might see, ideally in an animated visualization. So I might imagine I have data here, I've done maybe an experiment, I have a control and a treatment group, and so what I can first do is create sort of alternative instantiations of this data using bootstrapping or resampling with replacement or parametric bootstrapping, so resampling from distributions I fit to the data, so that I have these alternate versions that I could have gotten if I repeated data collection. I can then show each of those as a separate frame and combine them in an animation where I'm actually allowing the user to viscerally sort of see what uncertainty looks like. It looks like, it's hard to focus on what exactly the expected value is because there's variance. And so there's a few kind of theoretical or empirical motivations behind these from the psychology literature and perception literature. So for instance, using temporal frequency to encode distributional information is something that it tends to be automatically decoded. So people have to attend to the visualization, but they don't have to be consciously thinking, how often did I see this move above this value, or how often is this greater than this? We sort of can form intuitions from ensemble processing. And then secondly, in cognitive psychology and judgment and decision making, there's a lot of work showing that framing uncertainty as a discrete set of outcomes can help people do better on things like classical Bayesian reasoning tasks by giving people a better intuition about what uncertainty actually means. And so these hypothetical outcome plots do that. So as an initial study, because these are very different, obviously, from the static uncertainty visualizations that we kind of rely on and that we think of as sort of the best that we have in visualization research, I did a study with, I think, 300 people, or about 100 per condition, where they made repeated judgments with these visualization types. And we looked at things like if we show them univariate distributions, so just a single variable, and we have them estimate things like the mean, or the probability that the value is above some threshold, or the probability that the value is within some range, how well did they do relative to violin plots and error bars showing standard deviation. And we found that the accuracy here was comparable for hypothetical outcome plots, except for when you're estimating the mean and the variance is very high in the distribution, because the line is just jumping around too much, and so you have more error. However, when it came to multivariate comparisons, there was a very large difference. So we asked people for what's called the common language effect size, or probability of superiority. This is thought to be sort of a way that people can better think about effect size, where you ask them, if I were to take a random sample from these two variables, what's the probability that one would be greater than the other? And so we found that people were terrible, both with error bars, but also with violin plots with these types of judgments. Variables were independent here, so there were no sort of hidden correlations messing them up. And people who used HOPS did 35 to 41 percentage points better, or 35 to 41 percentage points lower error. So there's a very big difference, and I think the hypothetical outcome plots better express joint probabilities. More recently, we've been motivated to sort of think about the kinds of applied inference tasks that you might see, for instance, in the media. So we've looked at kind of how do journalists express uncertainty, and thought about a little bit what those applied inferences look like. And one case where we were motivated was this task that's put forth in the New York Times use of hypothetical outcome plots. Whoops, my animation keeps stopping. Where they were trying to get people to think about, you have these monthly job estimates for the year that are used to evaluate, is the economy or is job growth going up, or is it staying steady? And you can have an underlying trend of growth, but you can see something based on sampling error that looks different, or vice versa. So kind of giving people intuitions about how much sampling error impacts what you might get if you took a random sample of job growth estimates. And so what we did was translate this task into a two alternative forced choice task, where we're going to show people over many trials these hypothetical jobs numbers for the year, monthly estimates of jobs added to the economy, and then we're going to show them some reference uncertainty visualizations on the right here, showing the no growth model and the growth trend model, and we're essentially asking them which model is more likely to have produced the sample on the left. We frame the task as judging headlines, so your newspaper editor, and which headline would you apply to this particular set of jobs estimates, but the actual task is just what what's more likely to have produced the sample we see, which I think is common as well in analysis settings. So people did many of these trials, and we used a procedure where we wanted to really be able to fit what's called a psychometric function, a technique from psychophysics, to the data that they were producing. So we wanted to understand basically how accurate are they at different levels of underlying difficulty for these stimuli. And so as I said, we were varying, or we were using different uncertainty visualizations. So we tested in a first study error bars versus these bar hypothetical outcome plots. And we basically dynamically gave people stimuli that were, they varied in sort of difficulty, but they also made sure that people got enough of these very difficult trials based on their own abilities. And then we were able to fit these functions that kind of describe accuracy as a function of stimulus intensity. And here the stimulus sort of difficulty or intensity is the probability that the set of values we're showing you was produced by one model over the other. So how strong was that signal? And what we found was that people who used hops compared to error bars in our first study were more accurate at lower levels of underlying kind of signal in the data, or they were able to be accurate for smaller amounts of actual information. And so then we also wanted to understand, well, this was for these bar hypothetical outcome plots and error bars. So what happens if we change the static uncertainty visualization to one that also uses a frequency framing? So what if we show people an ensemble of lines representing these monthly job estimates? They're not having to deal with kind of a continuous encoding like an error bar. And we tested that against, maybe these stopped, hypothetical outcome plots using lines that actually varied in speed to try to understand kind of what's the mental process, how quickly can these things go and still have people form these ensemble sort of judgments. And we found here that, again, the hypothetical outcome plots allowed people to be accurate at lower levels of stimulus intensity or at more difficult stimuli, but only in the case in the middle here when the frame weight, I think, was between 400 and 500 milliseconds. So when the hypothetical outcome plots are moving extremely fast, people were not any more accurate. And so there's some sweet spot here in terms of how we're presenting the hypothetical samples. And I think there's a lot more work to do here, both on other tasks, but also on how do you parameterize these things. One thing I would just want to point out briefly is that with this approach, it doesn't matter what kind of visual encoding you have that you're working with. So something like this is from the New York Times. They were showing how different GOP members ranked going into the debate, so who would be in. It would be very hard to add an error bar on top of something like this or encode it in another visual variable, but you can use any time that you can resample your data and create multiple possible versions of what you might see, you can do this. So I'm going to skip this slide. We've also been looking at, in the case when you have static visualizations, does a discrete framing work? In the case where you can't use, for instance, hypothetical outcome plots because of quick decision making, basically we find that that is true. There's also an advantage there. But I now want to bring it back to this vision that I sort of started with of kind of putting these pieces together and thinking about, could we actually model visualization or data interpretation in these kind of casual contexts using Bayesian inference, and what do we learn from that? And so there's two kind of things or ways in which I'm thinking about this Bayesian inference framework. So if we can elicit priors, we know something about the data and the likelihood, we can kind of first use it in a prescriptive way to look at sort of what do we think people should have done and what did they actually do as a way of sort of evaluating visualization designs. But I'm also thinking about this in a less prescriptive way, in a way in which we don't necessarily assume that people should be perfect Bayesians, but instead we begin to use this framework to identify what other influences might keep them or explain why they're not doing perfect Bayesian inference with a visualization. So things like maybe they don't trust the source of the data, or maybe they're lacking the graphical literacy. I think often in visualization evaluation, we sort of have a hodgepodge of different instruments that we're using, and I think we can begin to quantify things all within one framework by thinking about data interpretation as Bayesian. And so the work I'm doing now in my lab is actually looking at Bayesian models of cognition, but applied to everyday data interpretation. And so one thing you might have noticed is that when you're truly doing Bayesian inference, you need a prior distribution. So an actual distribution over possible values that whatever you're guessing, say the job growth rate, might take. And what we were doing in the studies I showed was just getting sort of someone's maximum likelihood estimate. So we're just getting a single kind of salient guess. The question of eliciting true priors gets more complex. We're thinking now about, for instance, other types of encodings. How would you actually get a probability distribution over values from some of these other ways? Do you have to move to a more abstract format to elicit a prior graphically? So do you have to have someone draw a probability distribution? Or can you do it more naturally? And this question has led us to then thinking about, well, what is the actual format that people's mental representations of uncertainty in data-driven phenomena take? So for instance, do people have a full mental distribution of all of the possible values for the job growth rate this year? Or do they only reason in terms of a few sort of salient samples that they can think of? And here there's research in Bayesian models of cognition as applied to other sort of low-level cognitive judgments and perceptual judgments that suggests that in a lot of cases people might just reason in terms of samples. So they're not sort of walking around with these full representations. The common example from some of the literature there is that if you ask people to tell you how long a cake needs to bake, given that it's been in the oven some amount of time, people can be very accurate in aggregate at doing that, almost as though they know the true distribution of cake baking times. But on an individual level, they appear to be reasoning in terms of, I know that some cakes take 30 minutes, and I've also made a cake that took 50 minutes, and then they sort of deal with this small set of samples. So there's basically interesting questions about, what format do these things take, and how do you elicit them naturally? And one of the places the hypothetical outcome work kind of aligns here is that if people do reason with a few samples about these kind of phenomena, which is what we've been finding in our current studies, then you can actually just ask them to draw hypothetical outcome plots and also use that to express uncertainty. And so you sort of have this framework for helping people think about uncertainty and what they knew coming in, but also seeing uncertainty in the data. So getting a few samples, we then fit those samples to distributions that represent their priors. And so there's a little room for error or degrees of freedom in that fitting process. But there's also a lot that we're learning about sort of more information that you get when you actually can represent a true prior for a person. So things like reasoning about the perceived sample size that they saw when they looked at the data based on properties of the distributions we're fitting. So for instance, a beta distribution. You can look at the parameters of that distribution and actually get a sense of what did they perceive the sample size of the data to be and look at how off they were. So for evaluating uncertainty visualizations, I'm excited about kind of the possibilities here, using this kind of framework to think about design. So what could people like data journalists do if they knew more about what people believed data should look like? Could that help them design a visualization that was more sort of maximally effective? And there's obviously also exploratory analysis type applications here where if we know something about what people are expecting to see in data, can we better recommend what they should look at when they have a limited amount of time for analysis? And then finally, there's also questions about collective intelligence. So in some of the work we're doing now, we're looking at how good are people at predicting data, both in aggregate and individually, and how Bayesian do they appear to be at these two levels. And we definitely see instances where collectively people appear to be doing the right thing with data in a visualization that they're presented with, but in the individual level, not necessarily. And so there's interesting questions about how do you bring people to be sort of more rational at the individual level, or how do you explain why they're not, and is there some reasonable explanation? So I'll stop there. I'll leave you just with the takeaway. Prompting reflection on people's prior knowledge is not a bad thing when you're presenting data to them. And showing uncertainty through possible outcomes is also effective, and we can use this in visualization use to model that, to design visualizations and evaluate them. So thank you for your attention. Oops.
So we should have some time for questions. Questions for Justin?
Sure.
So the part of your talk that was about people interacting with other people's opinions, senses of
Right.
Did you ever run any sort of experiment similar to that, but on a subjective topic? So say one in which there isn't data that is correct, but rather you're having people interact left side is this is how delicious on a scale of 1 to 10 I think vanilla is.
Yeah, right.
Chocolate is, and how does consensus then impact people's preferences?
Yeah, no, I haven't. I mean, I guess the setting we ran it on, the 2020 data was, I mean, it's sort of, there's no truth, but we did tell people there's a model, and so I don't know how much that affected it relative to something that's truly subjective and people know it. So no, do you have like intuitions about how that would change things? Yeah, well, I'm interested in what they are. Yeah.
Have you tried using this to model someplace where you have lots of different input, where you're combining data from multiple places, all of which affect the same thing? An extreme example of this would be climate change.
No, yeah, not yet. But I think I've heard just from talking to people who work with climate scientists how there's a lot of issues related to aggregating the data and how difficult it is to explain sort of uncertainty in predictions. And so I mean, that's definitely a case I want to look at is some of these realistic data sets. Do you have thoughts on exactly how that would change things?
Well, you have lots of different measurements. You have multiple things,
like multiple models making predictions? Or?
Affect the data. And a lot of these individual components have different levels of uncertainty.
Right, yeah. I am doing some work now on how people kind of combine sources of uncertainty. There is research out there already that if you have multiple predictive models with different uncertainties and they all kind of contribute, that people do things like just averaging. But the question I often hear from people who work with like actual climate scientists and other types of scientists trying to communicate uncertainty is that often you have a model, but you also know, and you have some quantified uncertainty there, but you know that there are factors that are not represented in that model. And so like meteorologists know that there are things like that didn't make it into the model. And so how do you communicate these two forms of uncertainty where you want people to look at the probabilities but also consider what's missing? It's kind of like small world uncertainty of the model where you actually can calculate probabilities, and this larger world uncertainty of like our model is just one possible thing. And so I think there's a lot of interesting questions there for visualization people to tackle, and just uncertainty communication in general. Yeah.
Do you have any experience with three-dimensional framework design and evaluation?
Not too much, no. You mean actual three-dimensional data or visualizations?
Yes, I've recently come up with difficulty designing one because I think that it is quite difficult for people to imagine the three dimensions. So I've been trying to make one of the dimensions be a result of the two other,
Mm-hmm.
represented two-dimensionally. But I'm just concerned about the comprehension and interpretation.
Yeah, so 3D visualizations from a perceptual perspective are often not very effective. It's harder to read just individual values from them. Trying to think, Arvin might know more recent research on whether there are benefits to that as well. In general, in visualization research, we try to shy away from actual 3D and we just stick to 2 dimensions, like a 2-dimensional plane, and then you use other visual variables to show additional dimensions there, like color and size. But it's a difficult thing for people to think through. Yes?
So I really like the idea of visualizations influencing someone's prior belief and generating a posterior.
Mm-hmm.
But I can see there being a danger in like trying to design a visualization that updates the posterior as much as possible. It sort of gets into like whether we want to
Right. Yeah. No, I think there's definitely a potential to use something like this to do that. Yeah, and one of the things I want to do is actually start working with journalists and build some sort of basic tools to see how they would want to do this and where they think it would help them in design, to get a sense of kind of, how would people realistically use that, and is that a danger? So yeah, I see what you're saying. My hope is that the benefits of something like this for evaluating in particular uncertainty visualizations will more so show us how terrible people are at it. So in the recent studies we did using these Bayesian models, it's just abundantly clear, looking at what people perceived as sample size and the actual sample size of the data, there's these huge discrepancies. And so in a lot of ways, I think it makes problems like that much more clear. So I'm hoping that that's kind of one of the main things that people find useful in design. But yeah, it's an open question, I think.
So unfortunately, we're out of time.
I'll, I guess, be here maybe for a few minutes. So
please
thank
join
you.
me again in thanking Jessica.
Thanks. So that was
Thank you so much. I really enjoyed that.
Oh,
My name is
cool.
Krista Johnson.
Nice to meet you. Are you a PhD student here or
No,
postdoc
I
or
actually do
faculty?